Hello, I am David Hargis, and I am the CTO for IDEX Health and Sciences Life Science Optics business. Chad, Byler, and I will be talking about our work on advanced illumination and imaging technologies for the life science instrumentation market. I will start with a brief overview of the applications. Then we'll cover some illumination concepts, and Chad will review our work on imaging systems. IDEX has strategically pieced together companies and component technologies over the years that comprise the optofluidic pathway. In the optics space, you may be most familiar with Simrock optical filters, Melloscrio lasers, Melloscrio precision imaging systems, and Finger Lakes instrumentation camera products. From an optics standpoint, that means we can design and manufacture all of the key components that make up a fluorescent microscope, including laser and LED illumination modules, focus tracking systems, diffraction-limited objective and tube lenses, the optical filters, and board-mounted sensors. Most of our life science products involve some form of light-induced fluorescence. Typically, the light source is a laser or LED that is tailored to a specific fluorophore for excitation, and then we image the Stokes-shifted fluorescence. Our focus the last several years has been in DNA sequencing and spatial biology applications, and more recently we're looking into proteomics. This is an example of the types of systems we work on at IDEX Health and Science. It is a step and repeat epi-illumination system used in DNA sequencing and spatial biology. The customer typically has a biological sample tagged with fluorophores that they would like to interrogate. The sample can be placed in a flow cell. Often the flow cell is partitioned into sample patches shown here as small squares. The goal then is to precisely illuminate and image these patches one at a time. To minimize crosstalk and other deleterious effects to the sample, we would like to only illuminate an individual patch. We call that the field of view. The faster we can perform these steps, the faster the customer has an answer and thus can achieve high throughput. Here we show the multi-channel laser LED illuminator illuminating through an excitation filter, a dichroic, through a precision objective onto the sample. The sample fluoresces back through the objective, through the dichroic, through the emission filter, and then in conjunction with the tube lens, you form an image on the camera. The higher irradiance on the sample, so say in watts per square millimeter, the shorter the required exposure time of the sensor and thus higher throughput. This diagram illustrates a little more detail on these types of systems. Since we design and manufacture these key components, we can analyze the system holistically and optimize and trade off each of these components for overall performance, including the illumination system, imaging system, and the filters. This CAD-Tune example here includes a 4-color hybrid laser LED illuminator where we use 3 laser diodes and 1 amber LED, generating a rectangular flat top distribution at the sample plane that matches the imaging field of view as well as the sensor field of view. We also have excitation filters and dichroics, an autofocus module, precision objective and tube lenses. Flow cell plane would be up here, a filter wheel for multiplexing, and then finally 2 cameras. So this system multiplexes 4 excitation sources with 2 active at a time and 2 camera channels. Now I'll pivot over to deeper dive on illumination systems. The 3 most popular light source technologies fluorescent microscopes are diode pump solid state lasers, direct emitting laser diodes, as well as light emitting diodes. When we start a conversation with a customer regarding their illumination system, these are some of the key attributes of the light sources we trade off relative to their specific system. The first two rows here are related to their spectral outputs. Since the main function of the illumination source is to excite a fluorophore with a specific spectral band, the availability of specific wavelengths is important. And DPSS is quite limited, whereas laser diodes and LEDs are readily available across the UV to near IR spectral range. The diagram at the bottom of the slide illustrates the power levels on the y-axis and wavelengths for direct laser diodes and LEDs on the x-axis. Both give pretty broad coverage other than the amber regime for laser diodes. So the customer has a fluorophore. In this regime, we typically have to use an LED. The next item here has to do with spectral width. So the narrower the spectrum of the source, the easier it is to excite the fluorophore and to separate the Stokes shifted emission. Here, DPSS lasers are the best, with laser diodes a close second, and LEDs being quite inferior for this attribute due to their broad spectral widths. The next item is temporal coherence, which can have advantages and disadvantages. The disadvantage of high temporal coherence for these types of illumination systems is it becomes more difficult to eliminate speckle and interference patterns that can cause noise in the illumination profile and the resulting image. Laser diodes and LEDs have an advantage here due to their short coherence lengths. Next item, in terms of power levels, DPSS lasers are superior in terms of their available visible laser power when you compare them to laser diodes or LEDs. Laser diodes are typically, reliable laser diodes are in the 100 milliwatt to 5 watt without having to go to multiple arrays. Étendue is very important for high throughput systems. As I mentioned earlier, high irradiance at the sample leads to less exposure time and thus higher throughput. So here, DPSS lasers and diode lasers have a tremendous advantage over LEDs due to the poor étendue of LEDs. Electrical to optical efficiency is another important consideration, as it can drive the overall system cooling requirement and thus the size and weight of the instrument. DPSS lasers typically have low E to O efficiencies, while LEDs, due to their poor étendue, can have low source to sample collection efficiencies. So direct laser diodes win in this category. Cost is always an important consideration, and thus LEDs and laser diodes are more popular than DPSS lasers for most fluorescent microscope applications. As I mentioned before, we have many years of experience in designing and manufacturing OEM illumination modules for various customers, including applications like next-gen sequencing, confocal microscopy, flow cytometry, and spatial biology. We can source reliable laser diodes and LEDs matched to the customer's fluorophores from tens of milliwatts to 5 watts of optical power. Our specialty is producing flat-top speckle-free illumination, achieving greater than 80% uniformity. This is the typical output of a multi-watt laser diode, and to the left here is what we get on the output of our beam shaping system. So basically taking what comes out of the diode through an optical system, and we can generate these tailored flat-top profiles. We design beam shaping optics to match the flow cell field of view. So if it's a rectangle, we can make high aspect ratio rectangles. We can generate line profiles as well as We've done some work in structural illumination microscopy. We also have developed multiple compact turnkey multi-channel illumination modules. We can combine laser diodes and LEDs into a single package. We have expertise in building drivers for complex laser pulsing protocols, also the thermal control that can be especially important for high power diode lasers. Here are two examples of fully integrated OEM illumination modules that generate flat top profiles, again tailored to the customer specific field of view requirements. The one on the left is a free space launch where the illuminator is placed close to a combining dichroic in the optical system and is injected directly into the objective. The module on the right is a fiber coupled version where the illuminator can be mounted remote to the optical system, which removes the mass and heat from the critical imaging system. These contain multi-watt laser diodes, drive electronics, combining optics, mode scramblers for spec illumination, thermoelectric cooler, and the fiber coupling and custom beam shaper. An example of the size is given here for a 3 laser fiber coupled system, about 80 millimeters by 80 millimeters by about 170 millimeters. And these can achieve sample irradiances up to 1,000 milliwatts per square millimeter. So that will cover our work on illumination modules. I will now turn it over to my colleague Chad Byler to discuss our work in imaging systems.
Thank you, David. Switching over to the imaging side, I wanted to talk about several aspects of custom imaging optics. To set the stage for what you might want in a custom objective, I'll start with revisiting a traditional one. Here you can see a very stereotypical microscope that you might have used in high school science class. It has preset magnification objectives and a common parfocal distance to work with the turret. These standards are used here, but also throughout the optical microscopy world, and are based on Royal Microscope Society standards originated in the 1890s. This sizing standard puts a hard limit on objective sizing and still to this day can lead to resolution and field of view being constrained. Another aspect of these objectives is that as the eye was the primary detector available at the time, and the stage could be moved to bring the item of interest directly to the center of field of view, the only portion of the lens that was fully diffraction limited was a limited field of view around the on-axis point. In modern microscopes, cameras replace the human eye, and every pixel is seen equally by data and analysis algorithms. As seen here, the field numbers of common architectures sometimes are drastically oversized relative to cost-effective, small pixel and small format cameras available today. This results in true field of views at the specimen that are significantly less than the assumed value based on the objective magnification. One of the aspects that is inherently tied to this field of view is the magnification. Normally what people used to buying off-the-shelf objectives default to is thinking about a higher magnification, meaning a higher NA. That is true within a family of lenses. However, as you look across different families of lenses, you can see a 20x, maybe a 0.3 or 0.5 NA, and there are even some high resolution versions up to 0.75 NA. That numerical aperture value is the real representative number of the resolving power of an objective. The equation for the commonly used Rayleigh resolution capability of a lens is shown in the upper right. Magnification, even though it is printed right on the side of the objective, is only accurate if paired with its intended tube lens with a focal length between approximately 160 and 200 millimeters, dependent on the brand. The field number is actually closer tied to the magnification and can be used to calculate the maximum field of view at the sample if you divide field number by the listed objective magnification. You can see here the performance of a self-corrected tube lens of 200 millimeters that might be representative of a standard 1x tube lens. The performance is itself diffraction limited. However, you can see residual amounts of spherical, coma, and lateral color in the upper right ray-fan chart. If you focus on the lower left corner in the optical layout as we flip slides, you'll see how a tube lens can be relatively easily redesigned to a shorter focal length. This is a 128mm focal length, which is effectively a 0.64x mag adjustment, turning a 20x into a 12.8x. This would exactly match a field number of 25 millimeters to now fit onto a 16 millimeter diagonal or a 1-inch format sensor. The unfortunate outcome is, without complicating the tube lens, the same residual aberration now leads to a worse than diffraction limited performance from the tube lens alone. This means that while you've reduced your camera pixel size, you have not reduced your aberration blur size. With light now potentially blurred across multiple pixels, you may no longer be achieving your expected full system resolution. On screen, you can see a listing of specs that would be common for what is considered a good 20x objective that fits into the over 100 years old established mechanical envelope I referenced, as well as maintaining a standard 25mm sensor coverage. An additional item that you'll see is common is adherence to a standard 0.17mm cover slip used in research labs everywhere. The questions that I have, and many of our customers have, is what if you want more? This is where custom lens design comes in. By releasing the constraints on these old preset standards, we can achieve very different specifications. Here I kept the 0.5 NA that sets the resolving power and the 1mm working distance, and changed everything else. A 5.33x magnification lens would normally not invoke visions of high resolution. However, in this case, the best way to think about it is that we took that 20x objective and gave you 2.4 times the field of view, or 476% more sample area imaged back to your rectangular sensor. While we're tinkering with a custom design, we can add other features, like increased cover slip thickness compensation to work with flatter and thicker flow cells, or change the nominal objective to lens separation to allow optimal performance even with a dichroic injection filter and a full mirror in the path length. The ZMAX output quad chart in the lower right shows 4 different emission bands from the green to the near infrared for this particular design, plotted as RMS wavefront versus the field. Here you can see that despite these other design advantages, it is still possible to achieve designs well below the 0.071 waves RMS diffraction limit. So, what I'd like to have people take away from this presentation is the following. When looking to go beyond an off-the-shelf offering, don't get constrained by existing products. Instead of starting with what mag you need, start with your sample, and how small a feature do you need to resolve. As can be seen in the top chart, higher NAs combined with shorter wavelengths can drive significant gains in your ability to resolve close-packed features. Next, what field of view do you need? Rather than a field number or a mag, just figure what is your optimal field of view to achieve the throughput you need. Third, what sensor do you need? The sensor that has enough pixels to match your lens resolution, while also having a high signal and noise ratio and a data transfer rate fast enough to keep up with that throughput, is the right one. With a custom design, your mag will just be the output of the division of your answer from number 3 by your answer from number 2. While there are many more details that eventually need to get answered during a custom lens design process, these 3 get you off to a good first order start on achieving your real spec goals. The last crucial piece of custom lens design, or any lens design, is the consistency of the build quality. There is an assumption that is often made, but rarely verified, that every lens received is effectively the same unless it got dropped or otherwise knocked out of alignment. A revealing study that was performed a number of years ago in our factory took a single lot of purchased off-the-shelf objectives that had the headline specs desired by a customer and measured their wavefront performance. The plotted lines in orange represent the on-axis through full field of view performance. While mostly achieving diffraction limited performance on axis, the full field of view performance just wasn't there. The subsequent design process produced a design with the same specifications, and its nominal wavefront performance is shown via the purple line on the chart. Then we measured our own build consistency of that design across the field, and our results are plotted in blue. Design, build, and test are equal contributors in achieving the throughput you're after, with an optical solution designed to give you consistent imaging quality across your whole sample. Thank you for your time and listening to our presentation today. David and I will be here for Q&A on any questions you have on illumination and imaging systems and components for the remainder of the 30 minutes.